and from that raw data you try to dig out the precious patterns or precious information, then it becomes data mining. In one of my slides I'll shortly show you that you know the amount of data must be huge in order to qualify to be called as data mining, because if it is too small a data, then digging out precious metals, that becomes pretty trivial. So we're looking at large amounts of data, and obviously the World Wide Web itself is a huge collection of data, so it makes it more pertinent to do the data mining on the World Wide Web, and that is when it becomes mining the World Wide Web and searching the World Wide Web. So let us first take up the motivation. I hope you have seen the slide change. Can anybody respond? Can you see the slide?
Yes.
Okay. So this is my first slide of presentation, which is about the motivation. The world has become a global village. Yeah. The world has become a global village. Everything is on our fingertips. We try to dig out information. We try to search for it. There is a need to discover the information in a systematic manner. In fact, we are flooded with information. We are overwhelmed with information. But obviously, we have to, discover that information in a systematic manner so that we are not, we don't get the diarrhea of information. That is the idea. So a few domains I've taken, like for instance, in e-commerce, for the business to business collaborating. Can anybody mute it? Please mute the microphone. So business to business collaboration, there may be a company which is preparing conference bags, and they have all the expertise except for the printing of the logos of the conference on that bag. So they will be looking for a collaborating partner. So that is where they will be searching for the information of such a company which can do the logo printing for them. Likewise, there is a company which is printing greeting cards. So they are looking for new and new floral patterns. So there is a business to business collaboration, and there is search involved in it, so that they are able to land up in a suitable partner, suitable collaborating partner. So that was the example of motivation from business to business collaboration. Let us talk about consumer to business. Suppose there is a consumer who's looking for attires of a particular brand. Somebody who's looking for a vehicle with given specifications in terms of the seating, in terms of the fuel efficiency, in terms of the transmission, and so forth, right? Similarly, there is a sportsman who's looking for a specific sports good, of a brand or of a specific requirement. So that is where consumer to business will also require searching the information or discovering the information. Consumer to consumer, looking for a second-hand vehicle, searching for a home for renting or for buying, trying to sell some second-hand goods, it all comes under the purview of consumer to consumer. So in all these examples that I've given, and so many more examples could be given, you need to discover the information in a systematic manner. Then only you will be able to reach to the precise piece of information. So the bottom line is, which other place could be better suited for this resource discovery than the web itself? So that is why the idea of web searching crops up, and I'll elaborate on it in my subsequent slides. Before I proceed any further, there is one concept point that we must clarify. There are two terms which we use interchangeably, like internet and the World Wide Web. So we must be very clear about the difference between the two. Internet is the infrastructure. In fact, this is the acronym for interconnection of networks. So the hardware which is available, that is internet. Maybe with some system software which, facilitates the data transfer between the connected computers. So there may be a network of computers, there may be another network of computers, and when you connect the two networks of computers, it becomes an interconnection of networks. And when you connect all the networks in the whole world, it becomes internet or interconnection of all the networks over the globe. Now, this infrastructure may facilitate certain, certain operations. So World Wide Web is one of them. Others could be like emailing. You need the interconnection of networks for emailing to take place. Similarly, you may have file transfer protocol, FTP. Likewise, you have this www, World Wide Web, which goes under the hypertext transfer protocol. We all know about it, and we'll be talking about in the subsequent slides how do you harness that hyperlink structure. So World Wide Web is a facility which is built on top of the internet infrastructure. Now let us have a look at some definitions of data mining. You might be thinking, why so many definitions? I'll narrate an interesting, story that you must have heard in your childhood days. There were a few people who were, blinded, and they were asked to describe an elephant by touching it. So one of them, he touched the trunk of the elephant and he said, this is like, a tree branch. Another one touched the ears of the elephant and he said, it looks like a hand fan. Another one touches the trunk of the elephant and he said it looks like a wall. Why are they having different perceptions? Because elephant is huge. One person cannot encompass the entire description or cannot touch the entire elephant to describe it. Likewise, the data mining is such a huge concept. It encompasses anything and everything that has to do with anything with data. So therefore, several definitions have been given because one definition may not suffice. So one of the basic definitions is search for valuable information in large volumes of data. That is a very preliminary and a very basic definition. Let us elaborate on it. Exploration and analysis. So it is not just the exploration, it is the analysis also by automatic or semi-automatic means of large quantities of data in order to discover meaningful patterns and rules, right? So you see, of large quantities of data. Likewise, automatic or semi-automatic means, right? There may be completely automated process, but there may be intervention of the human beings too in order to make this exploration and analysis more meaningful. Right, in order to discover meaningful patterns and rules. So these are the keywords in this definition. Let us go on to the third definition. A step in the knowledge discovery in databases process, a step in the KDD process. So data mining may be seen as one of the important steps of KDD, which in turn, let me underline this KDD, which in turn is a non-trivial process. If it is trivial, there is no point in carrying it out, right? It has to be a non-trivial process of identifying valid, novel, potentially useful, and ultimately understandable patterns in data, right? So it is a step in KDD. It is a non-trivial process. It identifies valid, novel, potentially useful, and ultimately understandable patterns in data. Again, if you are familiar with the history of data mining, one of the data mining tasks is association rule mining, wherein you find out what all products have been sold together, right? So when people ran it, they found out that in these superstores, beer was being sold along with the baby products. That was something very shocking. Because beer is an adult product. It doesn't have to do anything with the baby products. But for some damn reason, these two things were being sold together. Prior to association rule mining, nobody knew about it. So their sales were not up to the mark because people were getting irritated for not getting the two products together. They were spaced apart. So in that sense, it has to be a non-trivial process, right? Putting all baby products together is a trivial process. Non-trivial process is putting beer along with baby products, okay, which otherwise doesn't hold any sense, but for some reason, the experience shows that they are being sold together. All those patterns in data that you identify, they have to be valid, they have to be novel, they have to be potentially useful, and ultimately understandable, right? So with these basic definitions of data mining, let us now move on. And one more thing. Everywhere it talks about large volumes of data, like large quantities of data. And obviously you can have all this only when you have huge data, right? So the bottom line remains that the best place to apply data mining is the World Wide Web. Now let us go on to the problem definition, problem of web mining. Let us define it. Firstly, we have to discover information from hierarchical organization. We all know that we have a home page, and then there are, children pages, right? For example, the home page of a university, and then there may be students information, there may be, teachers information, faculty information, there could be research information, and so on. So you organize data in a hierarchical manner, and this may continue. Right? This may continue until you come across a terminal page or the last page or the leaf page. So you have to discover this information from hierarchical organization. One may wonder, why is it organized in this hierarchical manner? Why don't you put the entire information in a single page? Why don't you put it like that? The answer is simple. If you put the entire information in a single page, firstly, it will not be well organized. A student, why should he be looking at the faculty information? Right. Similarly, a faculty who is, interested in some teaching information, why should he be looking at the research information, and so forth. Secondly, it is going to eat up your bandwidth. The student is just looking for admission. This is the student. He's looking for the admission information, right? So why should why should this student over here look for the admission information along with downloading the rest of the things? Okay? So organizing in a hierarchical manner is going to make it better organized and also saves you some bandwidth. But then when it comes to web mining and web searching, obviously this hierarchical organization has to be, traversed through in order to get the entire information indexed and searchable. Second point is precise information, no less, no more, with proper ranking. What happens if you are giving extra information in response to a query? You are overwhelming the user with the information. Obviously, he's not interested in that much information. On the other side, you can't deprive him of relevant information by cutting down on the web search results. So the information has to be precise, no less, no more, right? And that too with proper ranking. If you give the precise piece of information, but the ranking is not proper, then again there is that problem. He may be looking for the first document and doesn't find it interesting or relevant, so he may abandon your search engine, right? So all these 3 points, no less, no more, and with proper ranking, right? With proper ranking, all these 3 are important whenever we are designing a search engine. Now let us talk about the 2 resource discovery paradigms on the World Wide Web. And these paradigms emerge from the way people are looking for the information or discovering the information. There may be this, novice searcher who is a beginner. He doesn't know precisely what keywords I should look for. So he will go for browsing the information. And then there is some expert searcher who knows precisely the keywords that he's looking for, so he may go for searching. Let us take the analogy from a book. Suppose the World Wide Web is a book wherein somebody who is well versed with that topic, what he will do? He will turn the book upside down, he'll go to the end, and he will spot the index terms given at the end of the book, because he precisely knows what index term he's looking for. So accordingly, he will go to a page and look for the information that he required. Now there is a novice or a beginner who is new to that area, alien to that area. He doesn't know precisely the index terms. So he cannot take the information of the index terms provided at the end of the book. So what he will do, he will browse. Browse means turning pages, right? One after the other. So he'll browse through the book in order to reach the information. So browsing is not a big deal, but searching is, because you have to provide precisely the index terms, which is not a trivial process, let me say, which is a non-trivial process. In the subsequent slides, we will see that. Now, when it comes to searching, this searching has got two distinct paradigms: content-based and citation-based. We will discuss them one by one. So let me move on to the next slide. This is the architecture of a typical web search engine. The user interface, whatever query is issued by the user, suppose this is the query given by the user, it goes to a query processor. This query processor references a database. It doesn't happen, this query goes directly to the World Wide Web. No, it doesn't happen like that. It doesn't happen like that. It goes to a database, a pre-built database. And this database, it keeps getting updated by a module which is called the crawler. You know, a web crawler is a software which keeps crawling the web on a periodic basis and keeps updating this database for the user's query to reference at, right? So crawler is that piece of information. It may take weeks together. For the largest Linux cluster in the whole world, it may take weeks to crawl the web once. And whenever it is crawled, the database keeps getting updated periodically. So whenever you are searching, you must be assured that the information that you have got may be a few days old. It is not the current one. It is a few days old information. Now this database brings out that information according to that query, and scoring module ranks that information before presenting it to the user. So this is a very coarse block diagram of a web search engine, right? Query is issued, query processor references the database, database gives out the information to a scoring module, which is ranked according to the scores and presented to the user interface. And on this side, the crawler keeps updating this database by crawling the World Wide Web on a periodic basis and on a frequent basis. Now let us talk about the content-based web search. As I said in this slide, that there are essentially two paradigms, content-based and citation-based. So let us first take up the content-based approach. We are taking the content-based approach. The basic instinct in the content-based web search is that contents of a page are the best descriptors of that page. Obvious, you know, to begin with, it is very obvious. But to get the index term of a given document is a non-too trivial task. As human beings, it may be trivial. If you provide me with a page of information, I may go through it, I may comprehend it, and I may identify the key terms pertaining to that document, pertaining to that page. But what if you want to automate this process? Suppose that piece of text I'm inputting to a software and I want the index terms to emerge out of it. How easy or how difficult it will be? We will see in the subsequent slides. For example, Yahoo search engine relied on the human intelligence to get this indexing done for quite a significant amount of time. I'm talking about the initial days. Later, it happened that the World Wide Web grew so huge that employing human intelligence became a non-scalable solution. You cannot go on employing human beings to read each and every page on the World Wide Web and come out with the index terms, right? So this is a non-scalable solution. Equivalently, we may have to employ the complex natural language processing techniques to automate the job of indexing, but then in this case, it will become computationally intensive. NLP algorithms are not, easy to run or easy to implement even. So it becomes too difficult. In fact, crawling may get easier than the natural language processing to be done on those web pages. So what people have done, they have researched on some easier techniques, and they have borrowed from the information retrieval community of of researchers, and they have employed those techniques into the World Wide Web domain to carry out web mining. So let us take all those techniques. But before that, before we actually go on to content-based web search, we will have to do pre-processing steps, a couple of pre-processing steps. First one, text pre-processing is a prerequisite for the application of any content-based technique. Why? You will appreciate shortly. First of all, removal of stop words. The words that have very little semantic content. They are frequent homogeneously across the whole collection of documents. They are generally the prepositions or articles like the, and, for, etc. If you simply go on by counting the frequency of a word in a document as its index value, then these words, the, a, and, for, will have the largest frequency, whereas they have very little semantic content. So they don't qualify to be good keywords, right? So you have to strip off or remove such stop words before you actually employ the content-based techniques. So for that, there is a standard list of stop words, but that will be language dependent and that may be context dependent also, right? Suppose I have a corpus of documents on computers. So the word computer will become a stop word there because every document will have a stop word, will have computer in it. So there's no point in giving computer as the index term for every document. Instead, you can take computer as the index word of the entire corpus. That I can understand. But giving it for every document, the computer as the index word may not make much sense because they're all about computers anyway. So you may have a standard list of stop words. Stop words may vary from language to language. For English, I have given the information. For Urdu, Hindi, any other language that you may want to work with, you will have to figure out the list of stop words. And those stop words, even for a language, may be context dependent. So that is the first text pre-processing step, removal of stop words. Second may be stemming. All the words with the same root are reduced to a single form, stripping each word of its suffix, prefix, or infix. Words are reduced to their canonical form, to their standard form. I've given the example. Borrow, borrower, borrowed, borrowing. All would be reduced to the stem word borrow. So that is why the name is stemming. It is, like a branch which may have sub-branches, right? You may have sub-branches. So you want to basically cut down on these sub-branches and you just want to retain the stem word, right? So that is what you're doing. You want to cut down on ER, you want to cut down on ED, you want to cut down on ING, so that all these words are reduced to their stem word or the canonical form borrow, right? If you don't do this, what will happen? Suppose a document contains borrower, borrowed, borrowing in different forms, but not containing borrow, then in that case, when I'm launching a search with the keyword borrow, this document will not return because it has variations of borrow and not the borrow as such. So that is why stemming is important. The burden of being very specific while forming the query is thus taken off from the shoulders of the user. A well-known algorithm for carrying out word stemming is the Porter-Stemmer algorithm. And as I said earlier, it depends on the language of the document. So whenever you are doing content-based web searching or web mining, you have to do these text pre-processing steps. Number one is the stop word removal. The other one is stemming. Okay. Now, after you have done these text pre-processing techniques, let us go on to look at some of the content-based techniques. First of all, the term frequency. The frequency of a word in a given document is a good measure of its importance. Obviously, this is valid only after text pre-processing. Otherwise, a and the, for will have the highest frequency and they will emerge as the keyword of every document in the world. So that is why do text pre-processing and then count the frequency. Now, should frequency alone be a criteria? No. We need to add another component to it, which is called inverse document frequency. Term frequency, inverse document frequency. so that we are looking for such index words which are frequent in the current document, but not so frequent in the rest of the documents. That is the concept. And this is borrowed from the information theory. Information theory says that the content, the information content is inversely proportional to the probability. If there is an event which is least probable and that occurs, it makes the news. It has got the maximum information in it. Whereas an information which has, a very high probability, it doesn't make news. For example, if I say that sun rose in the east today, no newspaper will publish it as a news, because that is, the probability is almost a certainty. It is 1, right? So it doesn't form a good news. If for some damn reason sun rises in the west someday, that will be the headline of every newspaper. Why? Because the probability was very low. Likewise, the document should be frequent in one, the keyword should be frequent in this document, but should not be frequent in the rest of the documents, so that the uniqueness is gauged. Uniqueness of that keyword to that document is gauged, is measured, and hence the relevance. If it is unique to that document, it has got more relevance to that document. So this is the formula for term frequency, inverse document frequency. Frequency of the word in that document normalized by the maximum frequency of any word in that document. So this is the TF part. This is the TF part, term frequency part, right? And this is the IDF part. This is the IDF part. Log row by row W, where row is the total number of documents in a collection. If I'm talking about the World Wide Web, then the total number of documents on the World Wide Web divided by the number of documents that contain that specific word W, right? So log row by row W. Suppose row and row W are equal, which means every document in the collection has that word. Uniqueness is missing, right? What will happen? Row and row W being equal means log 1. And log 1 is 0. So even if the frequency of that document is too high, still log row by row W will reduce it to 0. So there has to be a huge gap between row and row W. So what is desirable? That FW should be as high as possible, preferably FW max, because that is the maximum that can happen in that document. And row by row W should have the maximum difference, right? It should have the least difference. It should have the maximum difference, row and row W. Then only it will qualify to be a good index keyword. I'll take the example, a numerical example later. But before I proceed, there is a finer point that I need to discuss, right? Why did we do stop word removal if TF IDF would have done the same thing? A and the for would have the least value, because every document will have A, every document will have the, every document will have for. So log row by row W will become 0 anyway. The other way around, why don't we, why at all do we need to do inverse document frequency when we already have done the stop word removal? In fact, both these steps are important. Obviously, log row by row W will be computationally intensive. It will take some computational time. So why, in order to strip A and the for, you need to do calculation? They are very obvious stop words. So remove them in the beginning itself, right? That is one part of the answer. The second part is that there may be, as I said, context dependent, right? Computer may be frequent in all the documents. If W is computer and row W are equal, it'll get 0. But I can't put computer as a stop word, because in other corpus, in other collection of documents, computer may not be frequent across the documents. Suppose I have a collection of documents on literature. In literature, computer qualifies to be a good index word. On a collection of documents on computer, the word computer doesn't qualify to be a good index word. So that context dependence requires this inverse document frequency to be done, right? So this is just the description. FW is the frequency of the keywords W in the document. FW max is the maximum frequency of any word in that document. Row W is the number of documents in which this keyword occurs. This should be, I'm sorry, this should be row only. Let me strike it off. It should be row only. Total number of documents in the collection, right? So just it is a simple formula. Try to memorize it. FW by FW max, this is normalized. Log row by row W, this is IDF. Yeah, because I'll be using it in my subsequent slide for a numerical example. So you must be well versed with this. Another approach, one approach I have, in fact, two approaches we have seen. Term frequency is one approach. Then term frequency, inverse document frequency may be the second approach. The third approach that I'm going to talk about is vector space model. In this, we assume an n-dimensional vector space with one dimension for each term or for each keyword. So that will be a huge dimensional space. All the words in the dictionary of a language, those many dimensions. Now, each document or query is represented as a term vector in this vector space. In that huge dimensional vector space, every document or query will be represented as a term vector containing the components of the words that it particularly has. Each component of the term vector is either 0 or 1, depending on whether the term corresponding to that axis is absent from or present in the text, right? Just take this theory. Next slide I'll show it pictorially. The similarity between a document and a query is the dot product of their term vectors. We can also calculate the angles between the term vectors of the query and the documents. Now let me show it pictorially. Suppose I am talking about a language which has just 3 words. In order to make it simple and understandable, suppose I have a language which has just 3 words, W1, W2, W3. So I'll have a three-dimensional space, Now every resource and every query will be represented by a term vector. Suppose the query contains W1 and W2, right? So it will be a term vector with a unit vector in this direction and a unit vector in this direction. So essentially, Q will be W1 cap plus W2 cap, right? A unit vector in the dimension W1, which is plotted on x-axis, and a unit vector in the y direction, which has the word W2. R has the components in W1 and W3. So correspondingly, R, this is a vector. Q is a vector, right? Similarly, R is a vector. So R has W1 cap plus W3 cap, right? Now, if I find out the cosine of the angle between them, that will be the similarity. Suppose they had been overlapping. Q and R had been exactly the same. Suppose there is some R1, which is the same as Q. Then they will be overlapping. The angle between them will be 0, and cosine of 0 is 1, maximum similarity, right? Let us take the other extreme. Suppose this contains Q110 and there is a resource which has a unit vector in W3 direction only, right? It has W3 only. So no keyword is common between them. Suppose there is some R2 which has simply W3 cap, right? So now they don't have any keyword common. So their term vectors are orthogonal to each other because this term vector is in the XY plane, whereas this one is in the Z direction. So they are at 90 degrees to each other. So if you try to find out the similarity between them, that will be the cosine of the angle, and the cosine of 90 is 0. So similarity is 0. So these were the two extreme points. Now, if you have to find out the similarity between this Q and R, you will have to find out the cosine of the angle between them, which will be somewhere between, 0 and 1, because the angle is neither 0 degree nor 90 degrees, right? So that is what the cosine of the angle between them will give us the similarity, right? So this is how the vector space model works. Over here, we have taken a simplistic case of vector space model in which we have just counted if it is present or not present. There may be a case where you have got how many times it occurs. So it may be 4W1 plus 3W2. If it occurs, W1 occurs 4 times and W2 occurs 3 times, it will be 4W1 plus 3W2. And then we can go a step ahead, and I can, instead of giving just the frequency and vector space model, I can have TF-IDF plus vector space model, right? I'll show you with the help of an example. So that is what I'm mentioning. Alternately, each component of the term vector is taken as a function that increases with the frequency of the term corresponding to that axis within the document and decreases with the number of documents in the collection that contain this term. We can also take into account the TF-IDF factor. The term vectors of documents must be normalized to 1 so as to compensate for different document lengths. We normalize. Why? Because the document may be of varying lengths. So I must divide it by the maximum frequency of any word in that document so that the document size doesn't play a major role. It becomes independent of the document size. Now, this interesting example will illustrate. Suppose I have a scenario in which I have 3 resources, 3 documents, R1, R2, R3. And I'm talking about 5 keywords, W1, W2, W3, W4, W5. And I say that W1 occurs in R1 5 times, W2 occurs 0 times in R1, W3 occurs 8 times in R1, W4 occurs once, and W5 occurs thrice in the resource R1, right? Likewise, W1 is occurring 6 times in R2 and 4 times in R3. W2 occurs 0 times in R1 anyway, 4 times in R2, 7 times in R3, and so on. W5 occurs thrice in R1, once in R2, and 3 times in R3. Now let me try to get the term vector corresponding to R1, R2, and R3. How do I write the term vector corresponding to R1? See, this is the TF-IDF formula. It says, I'm talking about W1. You see W1 cap, right? So it says 5 divided by the maximum frequency, which is 8. So 5 by 8 log row by row W. This W1 incidentally occurs in all the documents. So row W is 3 and row is 3 anyway. Row is 3, right? Because we have 3 documents, R1, R2, and R3. So row W is also 3. So it will be log 3 by 3 W1 cap. So this will be the amplitude in the W1 direction, which will be decided by the TF-IDF. So now both the things will be clear now. The vector space model plus TF-IDF. What do I do about W2 cap? It will be 0 by 8 because the frequency is 0, and log 3 by 2. Why? Because total collection is 3, but it occurs in only 2 of them. So it is log 3 by 2 W2 cap plus 8 by 8 log 3 by 2. 8 by 8 because the frequency over here is 8 divided by the maximum frequency, which is 8 again, log 3 by 2 because it occurs in only 2 of the 3 documents. That is why log 3 by 2 W3 cap plus 1 by 8 log 3 by 2, again 3 by 2 W4 cap plus 3 by 8 log 3 by 3, again 3 by 3 because it occurs in all 3 of them, W5 cap. So what will be? It is R1 is 0 in the direction of W1. 0 is coming not because of the frequency, but because of the because of the IDF factor, right? This is coming because of the TF factor, term frequency factor. This is again 0. This is having some finite value 0.176, which is a combination of the TF as well as the IDF, W3 cap. This is again a combination of TF and IDF. Now over here you see that this value is higher than this value, right? Why? Because its frequency is higher. This had the maximum frequency, whereas this one had a lower frequency. So I've chosen such an example which illustrates all the points. So it becomes 1 by 8 log 3 by 2 will be 0.022 W4 cap plus 0. Again 0 because of the IDF factor, not because of the TF factor, but because of the IDF factor. So I get R1 as a vector having these components in the 5 dimensions, where the amplitude of every dimension comes from the TF IDF value. So I'll just repeat it. Whatever I have written, I just repeat it. R1 cap is 0 W1, 0 W2, 0.176 W3 cap, 0.022 W4 cap plus 0 W5. Likewise, I can find out R2. I can find out R3. For example, R2 will be 6 by 6. You see, R2 will be, because 6 is maximum itself. And again, log 3 by 3, right? So one thing you must have started sensing, that this log value will remain the same all through. If this is log 3, this will also be log 3 by 3, this will also be log 3 by 3. Correspondingly, all of them will be 0, 0 because of the IDF value. So log 3 by 2, log 3 by 2, log 3 by 2, log 3 by 2, 3 by 2, 3 by 2, 3 by 2, so on, right? Log 3 by 3 in the end. The second one has the frequency itself as 4. So 4 by 6, maximum value remains the same. Maximum value will remain the same throughout. 6, 6, 6, 6, 6. So 4 by 6 log 3 by 2 W2 plus 2 by 6. This is the frequency 2. Sorry. So 201. So 201. Correspondingly, this will be the numerical value. Coming to R3. Remaining parts will be same because the maximum frequency is 7 here. So everywhere I am normalizing with 7. Everywhere I am normalizing with 7. This comes the same throughout. This will vary. So it should be 4, let me see, 47033. 47033. Correspondingly, this will be the value, right? This will be the value of R3 vector, term vector. Now we know that the dot product, suppose I want to find out the similarity between two vectors. So Ri dot Rj we know is the amplitude of Ri into amplitude of Rj into cosine of the angle between them. Dot product is a scalar quantity, right? So this comes out to be a scalar quantity. So similarity between R1 and R2. Suppose I want to find out the similarity between these two. So for that, I'll have to find out the cosine of the angle between them, which will come out to be 0.447. How? This will basically be, cosine of the angle will be R1 into R2 divided by mod R1 into mod R2. So what is R1 into R2? This is basically 0 into 0. I have written here 0 into 0 plus 0 into 0.117, 0 into 0.117, 0.176 into 0.059, 0.176 into 0.059, 0.022 into 0, 0.022 into 0, and 0 into 0. So that will be R1, R2 divided by the amplitude. Amplitude will be square root of 0 square plus 0 square plus 0.176 square plus 0.022 square plus 0.00 square, right? Into the amplitude of R2, which again will be 0 square, 0.117 square, 0.059, 0 square, 0 square. So when you work it out, you will say that cosine of the angle between them is 0.447. So that sense, you can say that they are almost half similar or 44% similar to each other. So this example illustrates how the TF-IDF works and how the vector space model works. Now let me move on to Boolean similarity measures. Boolean similarity measure, you know, when you go to the advanced queries, the keywords are connected by logical connectors. I can say that analog and computing, which means I'm looking for all such documents which has analog as well as computing. To contrast, if I have a query which says analog or computing, then I'm looking for all such documents which has either analog or computing or both, right? You know, and or operation. There may be a case where you're looking for analog and computing, but no digital. So you can write X1 and X2 and x3 bar. So I'm looking for such documents which contains x1 as well as x2, and it does not contain x3. So you see, the queries may be, Boolean expressions. So it all boils down to finding out the similarity between Boolean expressions. So a query and a resource may also be, suppose I'm talking about a corpus which contains many documents. So the keywords of a particular document will be connected by AND connective, and for different documents will be connected by OR. So it will be an AND OR query, and the and or expression, whereas the query may have a negative term or a complement term also. So how do I find out? One of the ways to do it was Jacquard's coefficient, where you need to actually find out the documents, how many documents are common and how many documents are in the union. But this measure requires the actual result to the query. It is mainly useful as index of comparison and not for searching itself. So that is why I'm not devoting much time to it. Instead, what I'll talk about is the Radecki measure. In the Radecki measure, the Boolean expression is transformed into the reduced disjunctive normal form, which is the canonical sum of product form, a disjunction or of a list of reduced atomic descriptors. This is the expression, but let me illustrate with the help of an example. Suppose I have a query and I have got a resource represented by Boolean expressions. These are the terms connected by and or connectors, right? So I want to find out the similarity between this Q and R. So first of all, I need to convert this into its canonical sum of product form, which is the RDNF. So RDNF of Q will be T1 and T3 and T2 bar, right? So T1 and T2 and T3, or T1 bar, T2, T3, or T1 and T2 bar and T3. And for R, it needs to be multiplied by, we all know, T2 plus T2 bar in order to make a canonical sum of product form. Then only it will become T1, T2, T3, T1, T2, T3, or T1, T2 bar, T3, right? So I need to convert both the Boolean expressions into the canonical sum of product form, and then I find out how many terms are common and how many are in the union of it. When I find out the union, I say that they are 3. This term, you see, this term is common, and these two are common. So the union of the product terms is 3. The cardinality of the union of the product terms is 3. I have this term, I have this term, I have this term. But out of these, only 2 are common. So the similarity will be 2 by 3, which is 0.667. If suppose there is no term common in both of them, obviously similarity will be 0. And if all the terms are common, similarity will be maximum 1. So this was about the Radecki measure. There is a big problem with this Radecki measure. Converting a Boolean expression into the canonical sum of product form, or RDNF, is NP hard. Why? Because for every additional term, you have to AND it with that term, and it's, suppose I just wanted to have T2, so I'll have to do T2 plus T2 bar. If I have to have, suppose, T4 also, then I'll have to have T4 bar, right? As faculty members of computer science, you must be appreciating that over here there were just 2 terms, now there are 4 terms. If I add T5 plus T5 bar, there will be 8 terms, 16 terms, 32 terms, growing exponentially, which leaves it NP hard. So the very conversion of a Boolean expression into the canonical sum of product form is NP hard. Obviously, we need to look for easier technique, and that is attributed to 2 researchers, Lee and Danzig, who found out the similarity with just the sum of product form, which may be canonical, which may be non-canonical, right? And this was the expression that they gave, and I'll illustrate with the help of an example. But over here, the idea was, the problem was, conversion into the canonical sum of product form. Lee and Danzig said we do not require it to be converted into the canonical sum of product form. Just give us the sum of product form and we'll give you the similarity by using these expressions. So let us see. Example, T1 and T2 or T3. T1 and T3. This is R. This is already in sum of product form, so we need not do anything. We just need to put it into the canonical, into the sum of product form. Any canonical, non-canonical. So for that, I need to apply the distributive property. So it will be T1 and T3 or T2 and T3. So first of all, I'll find out the similarity between these two product terms by the formula given earlier, which says 1 upon 2 to the power a minus b plus 2 to the power b minus a minus 1. So I will see that how many terms are there in this but not there in this. So we see that since both the terms are the same, a minus b is 0. So 2 to the power 0. Similarly, b minus a will also be 0 because both T1 and T3 figure in these two product terms. So 2 to the power 0 again, it should be minus 1. I'm sorry, this should be minus 1. So it becomes 1 upon 1 plus 1 plus 1 upon 1 plus 1 minus 1. So these two cancel out, I get 1. Perfect similarity, and that makes sense. They were T1 and T3, so they should be similar. Coming to the similarity between the second component and this one, the second product term and this product term. 1 upon 2 to the power, how many terms are there? This is T2. T2 is there in Q2, but not in R1. So that is why 1 upon 2 to the power 1. Similarly, T1 is here, but not in this one. So again, a one term, right? So 1 upon 2 to the power 1 again. Again, this should be minus 1. It should be minus 1 because the very formula says minus 1. It says minus 1. So what it will be? It will be 1 upon 3. 2 plus 2 minus 1 will be 3. 1 upon 3, 0.33. So similarity between these two is 0.33, right? I take the average of that, and that will be the overall similarity between Q and R, right? So this was, so Lee and Danzig measure reduces time and space complexity from exponential to polynomial. I wish I had more time. I could have taken more examples, but let us now, continue with our further. What are the problems with content-based web search? Search engine persuasion or keyword spamming, because we all know that everybody is free to write his or her own homepage in the way he or she feels like. So what people started doing, they suppose in HTML, if I choose the color of the text the same as the color of the background, so that will be the invisible ink. I may not be able to see the word written on that particular page. So what I can do, I can create a page and I can write in that invisible ink a catchy word like car 1,000 times. So whenever anybody launches a query, my page will be at the top because it has got the maximum frequency, right? That will come at the top. Whereas when you will open my page, you won't see any information pertaining to car. So just as we have spam emails, unwanted emails, people started putting unwanted keywords in the invisible ink on their home pages, something which we cannot control, right? That was one extreme problem with content-based web search. The other extreme was, for example, the IBM homepage did not have the word computer on it for a good amount of time because they thought it too trivial to write the word computer. They thought that everybody knows that we are a computer company. They talked about, higher techniques, like they talked about RAID, they talked about networking, they talked about, RAM, but computer was too trivial. Now, if you do the content-based, IBM homepage will never emerge as a contender for the keyword computer. So this is another extreme absence of keyword. On one side, spamming with keywords, and the other side, absence of keyword, right? In order to do away with these problems, we started going for hyperlink analysis. hyperlink analysis is based on how people are pointing to my page through their links. So I'm not dependent on what I wrote. I'm dependent on what others are saying to me. You must have heard self-praise is no praise, right? Self-praise is no praise. So content-based like self-praise, I can go on bragging about myself. But what is important is what others are talking about me. That is what hyperlink analysis is. So this gives an unbiased factor to the ranking. We will shortly see. First such approach was Hypersuite prototype. That is a scalable system that uses content link hypertext clustering based on document contents as well as the link information. The similarity measure between the two web documents based on the links between them includes the measures of shortest path between the two documents, the number of ancestor documents that refer to both documents in question, and the number of descendant documents that both refer to, right? So that is how connectivity based web search started coming in, and it evolved into what is called the HITS algorithm, hypertext induced text searching. But for that, we need to have a model of the World Wide Web as a diagraph, as a directed graph. You know, web pages being the nodes and hyperlinks between them being the directed edges. So suppose a home page has a hyperlink from this page to this page, so that becomes a directed edge. Similarly, if there is a hyperlink from this page to this page, it becomes a directed edge. So all the web pages were modeled as nodes, and all the hyperlinks were modeled as directed edges of the diagraph, right? Now a page is important only when many other pages point to it. Alternately, a page is important if many important pages point to it, right? I may be a good page on computers only when other computer pages are pointing to me. Or I may be an important page on computer if giants like IBM, like HP, like Dell points to my page. Then I get that information. So I'm totally relieved of my contents. I'm more dependent on what others are telling about me by virtue of the hypertext. So with every page in this diagraph, I'll attribute two quantities. One will be the authority value and the other will be the hub value. The authority value of a page is equal to the sum of the hub values of all the pages that are pointing to it. Suppose two pages are pointing to it. So this will be, A will be the sum of the hub values of the pages that are pointing to it. And hub value of this page will be equal to the authority weights of all the pages that it points to, right? It points to this and it points to this. Okay, so that is why I have, that is what I have. The authority of a page, authority weight of a page is summation of the hub weights of all such Q pages such that Q points to P. So AP will be the sum of the hub values of all the pages that are pointing to it. This is AP and they are all H1, H2, so on, HM. This will be Q, right? So this will be Q, right? Conversely, the hub value will be summation of the authority values of all Q's such that P points to Q. Over here it was Q points to P and here it is P points to Q, right? So hub value is equal to the sum of the authority weights of all the pages that this page points to. So I can begin. Let us number the pages on the web as 1, 2, so on up till n and define their adjacency matrix A. Because directed graph will have the adjacency matrix. Set of all A values as a vector A will be A1, A2, A1. So A1 will be the authority value of page A, A2 will be the authority value of page 2, AN will be the authority value of page n. Likewise, H1 will be the hub value of page 1, H2 will be the hub value of page 2, and HN will be the hub value of page n. So in linear algebra, I can write that the column vector A is A transpose, where A is the adjacency matrix, into the column vector H. And the column vector H will be the adjacency matrix into the column vector A. You can verify for yourself. This is how you can write. In fact, what I've done is I have put this information into the form of matrices, right? Because it will be dependent on the adjacency matrix. If I go a step further and over here I substitute this H with this, so it becomes ATH, AT, AA. So this AA will come here, right? So this becomes A transpose into A multiplied by A. And H becomes AA, and if I substitute this A over here, it becomes AATH. Linear algebra tells us that when normalized, this sequence of iterates converges to the principal eigenvector of ATA for A and AAT for vector H. This can be proved using linear algebra. So what I can do, I can over here I can initialize the hub value and authority values by any arbitrary value. But the condition is the summation of all the authority weights should be 1, and similarly the sum of all the hub weights should also be 1. Then I update A1 is equal to the current values of H's, and H1 is equal to the current value of A's, right? Then I move on to the next page. And over here, I take the authority value as the sum of all the hub values and the updated value of this one, because this has already been updated. When I move on to the third page, I take the updated values of these two and the initialized value of these three. When I move to this one, I go on doing it and complete the cycle. Then I do it again. It will ultimately converge. This reinforcement process will ultimately converge, and linear algebra shows that it will ultimately converge to the principal eigenvector of ATA for the authority weights and AAT for the vector weights. Based on this, there was this clever search engine designed by IBM Almaden Research Center, and there was the involvement of one of our Indian colleagues from IIT Bombay, Professor Shauman Chakrabarti. I've met him, I've attended one of his tutorials. So he was one of the instrumental person in devising this mutual reinforcement of hubs and authorities and designing a clever search engine. But that clever search engine did not become a success story for a couple of reasons. I'll come to that a little later. Let me take on the success story, which is PageRank. This is the backbone of Google search engine, which has done exceedingly well in the past several years. The quality measure of a page is its in degree. Suppose there are total T pages on the web. We choose a parameter D, which is lying between 0 and 1, but a typical value of D might lie in the range 0.1 and 0.15. Why we do it? I'll explain each and everything. This is a beautiful, beautiful expression. If only you can understand it. Let pages P1, P2, PM link to page PJ, and let CPI be the number of links coming out of PI. Then I'll explain. I'll give the example. Don't worry. Then the page rank RPJ of the page PJ of this page is defined to satisfy D upon T, where D is a constant, T is the total number of pages, plus 1 minus D summation of the page ranks of all the pages that are pointing to J divided by their outgoing links. Right, you got it. The page rank value of the jth page is this constant D divided by the total number of pages. Why they are doing it? I'll come to that. Plus 1 minus D summation of the page rank values of all the pages that are pointing to page J divided by their outgoing links. Okay, just remember this expression. This is a wonderful expression. Note that the page rank forms a probability distribution over web pages, so that the sum of all web pages page rank will be 1. That is 1 point. This is probabilistically very valid expression. Page rank can be calculated using a simple iterative algorithm and corresponds to the principal eigenvector of the normalized link matrix of the web. A page can have a high page rank if there are many pages that point to it, or alternatively, if there are some pages with high page ranks that point to it. Right? In fact, let us talk about an example first, an analogy. You see, there are two kinds of research papers, a review paper and a technical paper. A review paper is like a good hub page because that points to many good technical papers. Whereas a good technical paper is like a good authority paper to which many review papers must be pointing to, right? This must make sense. A review paper is like a good hub page because this is pointing to many good technical papers, whereas a good technical paper is the one to which many review papers are pointing to, right? So that is the concept of hubs and authorities, right? Now, we all know citation. That is why, you know, this connectivity based is also called citation based approach. There are many names given to it. Once again, many names because it encompasses so many more things. So that is called connectivity based, that is called hyperlink based, that is called link based, that is called citation based. All these are synonymous. They're all the same approaches. So a paper is very important if there are many people referencing that page. So that referencing is the, you know, passing on the authority by the hyperlink, right? Okay. So now a paper may be important if there are many people who are referencing it. Also, a paper may be important if a Nobel laureate references your paper. So even though there may be a single reference, but since a person of the stature of a Nobel laureate references your paper gains importance, right? So it is not just the in degree, but the importance of the in degree that also counts, right? So that is the point I'm trying to make, right? For example, I write a technical paper and I tell all my students to reference my paper in their papers. Okay, many in degrees. But I must be a good researcher only when the stalwarts in my field start referencing my paper, right? So that is the idea. A page can have a high page rank if there are many pages that point to it, or alternately, if there are some pages with high page ranks that point to it. So before I go on to this question, let me take an example. A page rank is a model of user behavior. We assume there is a random surfer who is given a web page at random and keeps clicking on links, never hitting back button, but eventually gets bored and starts on another random page. Okay. Let me take the example first and then I'll come. Suppose this is a diagram. I've taken a diagram. Suppose this is my World Wide Web containing just 5 pages. Okay. A small example I'm taking. So I'm numbering them without loss of generality. I can number them as page 1, page 2, page 3, page 4, page 5. I can number them in any way. No, that is what I mean when I say without loss of generality. Now RP1, the page rank value of this page. I'm talking about page rank, so don't confuse with hubs and authorities. And that in fact is a plus point with page rank. I'll come to it. That it talks about just a single value and not 2 different values as hubs and authorities. It talks about just the page rank value attributed uniquely to every page. So RP1 will be D by 5. D is a small constant. 5 are the total number of pages. You see, D by T plus 1 minus D. Now see, this is pointed by RP3 divided by the total number of outgoing links, which is 2, right? So RP3 by 2 plus what is the other link? In link that is coming from RP5. So RP5 divided by again 2 because there are 2 outgoing links. So RP1 will be D by 5 plus 1 minus D into RP3 by 2 plus RB5 by 2. Because there are only 2 in links and both these in links are coming out from such nodes which have an out degree of 2. Likewise, come to RP2. RP2 is again D by 5 plus 1 minus D. Now look at it. It is getting 3 in degrees. One is coming from RP1 and RP1 has 2. So RP1 by 2, right? RP1 by 2 plus the other one is coming from RP3, which again has degree 2. So RP3 by 2 plus this is having RP4 by 3 because the out degree is 3. 1, 2, and 3. So RP4 by 3. So 3 in links coming from RP1 by 2, RP3 by 2, and RP4 by 3. RP3 again will be D by 5 plus 1 minus D. If you look at it, it is RP4 by 3 plus RP5 by 2. RP5 by 2. RP4 is D by 5 plus 1 minus D. It is having only one incoming link. So it will be RP1 but divided by 2 because RP1 has two outgoing links, right? And RP5 is D by 5 plus 1 minus D. RP4 by 3 because it is receiving from RP4 by 3 plus RP2 by 1 because the out degree of RP2 is 1 only. So this is RP2 by 1. Right, so this is how we write down the page ranks. Now if I take you to the, now you see this is how I'm doing. RPJ is equal to D by T plus 1 minus D, summation of all the page ranks divided by their outgoing links. Now this expression must have made some sense to you. The point I'm trying to prove is, suppose you sum it up. Suppose you sum all of them. Suppose I'm summing all of them. Summation I is equal to 1 to 5 RPI. 5 because there are just 5 pages is D by 5 into 5 because it will be D by 5 plus D by 5 times. So D by 5 into 5. These two will cancel out. Plus 1 minus D remains common. And then what I see is RP1 by 2 plus RP1 by 2. So RP1 by 2 into 2. Right, cancels out. RP2, you see, RP2 by 1. So RP2 by 1. There's no other RP2 over here. RP3 by 2 into 2. So RP3 by 2 plus RB3 by 2. So RP3 by 2 into 2, this cancels out. Plus RP4 by 3 into 3. So RP4 by 3 plus RP4 by 3 plus RP4 by 3. So this also cancels out, right? And RP5 by 2 into 2. So RP5 by 2 into RP5 by 2 plus RP5 by 2. So that becomes RP5 by 2 into 2. This again cancels out. And I've covered all of them. You see all of them have been struck off. Okay. So summation over all the pages on the web will be D plus 1 minus D summation again. This is summation again. This is nothing but summation again. So this implies that now you see this one will cancel with this one. Do a little bit of mathematics. When you open it up, it will be D plus summation this minus D summation this. Okay. When you take it on this side, it will become D summation is equal to D. So summation will be D upon D equal to 1. So this proves my point. This proves my point that, yeah, this point. The page rank forms a probability distribution over web pages so that the sum of all web pages page rank will be 1. Whenever you extend it to any number of nodes, to any degree, this will hold, right? Now, this can be calculated using a simple iterative algorithm, as we have seen in the case of hubs and authorities. We, initialize with some arbitrary value such that the sum remains 1. And then at every step, we need not normalize it. Automatically, the sequence of iterates will remain bounded by 1, will remain normalized by 1. And this will ultimately converge to the principal eigenvector. Now, talking about the random surfer, what do? We open up a page and then we read that page and there may be some hyperlinks. Now I click one of those hyperlinks that takes me to another page. There may be certain hyperlinks there, right? I can choose this one. I can go to this page. That is how I do the surfing, right? And this continues until a point of time when I get bored. This sequence I get bored with and I start writing another www whatever. Okay. The probability that we get bored and request another page is D. This is small constant, which is theoretically between 0 and 1, but practically it is around 0.1 or 0.15. It should have a low value of getting bored. Okay. What if I'm not bored? So this is the probability of getting bored, D by T. This is 1 minus D means I'm not getting bored. This is the probability of clicking a link over here. Yeah. The probability of clicking a link is equal to the page rank value of the page that it points to. Suppose this has 0.1, this has 0.5, this has say 0.01, and this is 0.02, right? So this will actually be the page rank value of the pages that this hyperlink points to. So the probability of clicking a link is equal to the page rank value of the page that it points to, right? It should not mean that every time I will be clicking the one having the highest page rank value. No. That is where we have to get a concept of probability in place. What do we mean by probability? Suppose I toss a coin, getting a head, the probability is 0.5, getting the tail, the probability is 0.5, right? What does it mean? If I toss a coin twice, am I going to get head once and tail once? No. Then what does it mean? If I toss it 4 times, am I going to get head twice and tail twice? No. Actually, this is the point that I'm trying to, get your concept clear with. When the number of trials tend to infinity, then the probability value is reached. If I toss the coin infinite times, then only 50% times it will be head, 50% time it will be tail. Let me illustrate it with the help of a joke, which is a learning joke. There was this patient who went to a doctor. The doctor examined him and said, I've got a good news for you and a bad news for you. So the patient said, give me the bad news first. The doctor said, the bad news is that you will have to be operated and your chances of survival is 1 in 100. Now this patient started crying. 1 in 100 is too low a probability. He said, wait. There's still the good news left. He said, what is the good news now? He said, the good news is that in your case, the chances of survival is 100%. He said, how can you be so sure? The doctor said, because I have performed 99 operations before and all of them have died. You are the 100th one, so you'll definitely survive. Does that what probability mean? No, that is the abuse of probability. 1 in 100 means that if infinite such operations are performed by different doctors across the globe, then 99% patients will die, 1% will survive. If that doctor had killed already 99 patients, it is very likely that he's going to kill the 100th patient also, right? So remember this joke, then you will get this concept of probability embedded in your mind forever. Now coming here, page rank value of this page being 0.5 means the probability of clicking this page is 0.5, which means if infinite web surfers land onto this page, if infinite, then 50% of them will click this page, 10% will click this page, 1% will click this page, and 2% will click this particular link. That is the concept of probability. So this page rank expression beautifully captures the model of user behavior. You are opening a page. The probability of clicking a link is equal to the page rank value of the page that this hyperlink points to. You go on clicking, never hitting the back button, right? Ultimately, you get bored and you start an altogether a different page. The probability of getting bored is D, small d, which is theoretically between 0 and 1, but practically it is low value 0.1, 0.15, right? So why PageRank is a success story? Because it beautifully captures the random surfer model. It is a sound probabilistic model, as we have, proved over here, right? As we have proved over here. And also, if you're familiar with the history of Google search engine, there was these two, PhD students at Stanford University, Larry and Page, Sergey Brin and Larry Page. Yeah, Sergey Brin and Page. So they came up with this expression. They were very excited about it. So once they came to know that there is some big industrialist visiting their PhD supervisor, so they were standing outside the office of their supervisor with their laptops in hand. By the time the industrialist came out and he walked to his car, on the way they explained this page rank expression to him. And by the time he got into the car, he got so much convinced that he pulled out his checkbook and wrote a check worth $100,000 and wrote "Pay Google Inc." Signed it with the date and handed it over to Brin and Page and drove away. Now they write in their biography that we were standing there astonished what to do with that check. That check sat in our drawers for good 2 weeks. After 2 weeks, we decided to open a company with the name Google. That is how only the check could be cashed. So they made a humble beginning. They made a Linux cluster. They crawled the web. They found out the page rank value, and slowly but steadily it kept rising and rising and rising. And it is now a huge success story. So this is attribute. There are many more things. I don't deny there are many more things, but this is the starting point. This Boolean expression, this page rank expression is the starting point in the success story of Google search engine, which is a very good model of web surfing. Now, let me give you an open research problem. You're all faculty members. You see, I said that never hitting back, but we quite often hit the back button. We all know we hit the back button, but that is not incorporated in the page rank expression of Sergey Brin and Larry Page. If somehow you can incorporate the model of hitting the back button also in the page rank expression, if you can accommodate, that will be a good research. So I'm also giving you a good research problem. Okay? So now let me conclude by saying that content based, you need to do text pre-processing first, right? Stop word removal stemming. Without that, content-based may not succeed. Content-based, we have seen TF-IDF, we have seen vector space model, we have seen Boolean similarity measure, but all of them have the flaw because everything is dependent on what I write on my page. I can do keyword spamming, or there may be a case, inadvertent case, where the keyword may be missing. The most important keyword may be missing, as was the case with IBM. So people started talking about connectivity or hyperlink based, wherein what others are telling about you. Okay, so that became more important. Okay, and that is how the success story started building up. Page rank expression, it became a beautiful model of the web surfer, and it is also a valid probability distribution. So it is not only mathematically sound, but also it is a very good model of random surfer. Okay, I think we can stop here. I can take questions now, because we're running short of time. Thank you very much.
Thank you for the nice session. So we have some questions. First one is, how come citation help in searching? Please explain.
Yeah, okay, that's a very good question. Let me tell you, whenever we do searching, first of all, we have to get the collection of documents on that topic. So we employ content-based technique to pull out all the documents in that pertaining to that keyword. Then ranking is done according to connectivity based. Which of these documents is most important, that will be ranked only if it has got a high page rank value. For example, I pulled out the documents pertaining to car, right? Okay. Let me, okay. Suppose I start doing the, yeah. Suppose I stop, what I was saying is, yeah. Suppose I put car many times in my home page, but page rank value of my page pertaining to car will not be high, because not many car pages are pointing to me, and not many important car pages are pointing to me. So that is how I start with content based to build a corpus, and then within that corpus, I do the ranking using connectivity based. I hope it's clear.
Sir. So we have another question. What optimization techniques are used for query processing?
For query processing?
Yeah, query processing, yes.
No, actually query processing doesn't require any optimization. Query processing is more putting it in a certain syntax. That's it. People may give it in different syntax. but you need to normalize into such a syntax, or standardize may be a better word, into such a syntax which is acceptable by the database. If you remember the very first block diagram the web search engine had given, when you refer to the database, it should be in a standard form, because database doesn't understand many varying forms. So query processing isn't done by any optimization. It is more done by the syntax, syntax validation. Yes.
Okay, sir. We have next question. What are the limitations of vector space model?
I told you one of the limitations that goes along with it is the limitation of the connectivity base, because in vector space model also you are content based, because there also you are heavily relying on the contents. If I write car 1,000 times, the term vector in the dimension of car will be that much more, and whenever anybody forms a query, that will be overlapping with my home page, or will be closer to my home page, and that will come out at the top, even though it doesn't have any information pertaining to car, right? So the limitations of the content base will apply very much on vector space model too.
So participants are also asking any alternative way of representing words in vector space.
Of representing what?
Words in
No.
vector space.
No, a single word will form a dimension. A single word will form a dimension in that vector space, but a document will form a term vector. Or suppose you are taking a document with a single word, it will essentially be just a unit vector in that particular direction only. That's it.
Okay, sir. Any other question from participants? Okay, thank you, sir. Thank you for the nice session. It was very valuable and informative session, and we at the Computer Science are very much grateful to you. Thank you, sir.
Okay. So I'll leave the meeting now, right?
Okay, thank you, sir. Now, dear participants, we have another meeting at 12 noon, so you are requested to join before 5 minutes. Thank you, all of you. Now, all of you can leave.